All right, good morning, everyone. So our first speaker today is Rinat Kedem, who will speak about integrable quantum cluster algebras associated with affine root systems. And before we start, there are a few people on Zoom following the talk. So if you have a question, use
the microphone. Thank you very much, and thank you for getting up so early in the morning to watch this talk, especially because it's a little bit apart from the subject of the other talks in this conference. So just relax, and maybe you'll learn 2 or 3 new techniques or concepts in this talk, so that'll be great. So for each affine root system, I want to describe a discrete evolution, which comes from, quantum spin chains, but really it comes from representation theory. So we already heard about Q systems and T systems yesterday and last week, so I'm not going to apologize too much about talking about Q systems. And those are the systems of interest, and I want to view them independently of beta ansatz and things like that. What I want to say is, okay, they have this structure, which is a cluster algebra structure. You can quantize them. And so they're discrete recursion relations, which I want to view as discrete time evolutions with a quantization into non-commutative variables. And then what I want to do is, since they are defined for every root system, affine root system, I want to find a uniform structure of why they're all integrable. And it turns out that one has to go through McDonald or Kornwinder theory to prove this. So it's a project that with Philippe we've been considering for several years, and they sort of come together in the end, and there's a nice uniform description of everything. And so I wanted to tell you about this. Okay. So the 2 techniques that you might learn from this talk are duality in McDonald theory and the notion of Cherednik's notion of Fourier transform. So sorry, I should have said that. Okay, so here's for SL2. We've seen this last week and yesterday. There's a T system and a resulting Q system. So you have the XXX model on the lattice, and you consider higher spin generalization of XXX. So the auxiliary space might have some representations on it, which is this is the K+1 dimensional evaluation representation on the auxiliary space. So people call these higher spin transfer matrices. And I'm just going to consider the combinatorial data in the transfer matrix. And so I have a family of commuting matrices. So I think Vincent mentioned this yesterday. So J has just got to do with a spectral parameter, zeta. So zeta is some non-zero complex number. And K is just which symmetric power of the fundamental representation of SL2 you take on the auxiliary space. So I'm just going to parameterize the family of transfer matrices by J and K to integers. And usually in spin chains, K is greater than or equal to 0. It doesn't make sense to consider K less than 0. And so this is the T system, which we've seen written yesterday, for example. It's exactly the same T system, only I put the -1 on this side instead of on this side. And then when you do asymptotics of thermodynamic beta ansatz, you need to consider the arguments in the quantum logarithms. You need to take the limit when the spectral parameter zeta goes to infinity. Then you lose this integer j. What was I saying? Okay, so I view this. Okay, this is some recursion relation for some q's. Okay, I view this as a recursion relation in time, a discrete time variable k. I just feel like doing this because I can solve it. And so it's a 2-step recursion relation. So if I give you some initial data, usually Q0 is equal to 1 and Q1 is the character of the fundamental representation of SL2. Then this is a discrete time recursion relation. And this is how I want to view it. So I understand this is a very different point of view than what we're used to consider. But it's possible to do this. It's possible to consider these systems. And in the end, it has something to do with the partition functions that Vincent was considering yesterday. So the combinatorial partition functions. You can compute them using these things. Okay, so as I said, I claim this is a cluster algebra mutation. Cluster algebra is controlled by an exchange matrix, which can be shown as, it can just be written as this quiver. It's the Kronecker quiver. It's 2 nodes and 2 arrows between them. And because of this, it has a canonical quantization. So I can write down a discrete non-commutative integrable equation, which is the quantum, I call the quantum Q system. So, and my goal is to solve it and to show that it's integrable. Okay, it's possible to show that it's integrable just by hand, no problem. The solutions are just some quantum Wronskians. But then I can also consider T systems and Q systems for SLN. So the T system for SLN, you have a family of commuting transfer matrices, and these actually depend on 2 integers, I and k. So you take the highest weight k, omega I, where omega I is one of the fundamental weights of SLN. And so these are known as KR modules. And so you put that on the auxiliary representation, the horizontal space. And you have a spectral parameter again. And so I have now a transfer matrix depending on 3 parameters, I, j, and k. J has to do with the spectral parameter. And the combinatorial system, so when zeta goes to infinity, so this is satisfied the Q system, which again, I think most people are used to seeing with this term on the other side, but that's okay. And then I have some boundary terms, T0 and Tn plus 1 should be equal to 1 because we're considering SLN, so the rank is limited. And then in the asymptotic, zeta goes to infinity, this becomes the Q system for SLN, which looks like this. Qi k plus 1, Qi k minus 1 depends on Qi k, and then the neighbors on the Dinking diagram of type A, I plus 1 and I minus 1. And so if I give you some initial data, you can consider this to be a discrete evolution equation in time k. And just if you happen to be curious, both of these have a cluster algebra structure. The T system is an infinite rank cluster algebra, and it has this quiver that goes off. This is SL3. So here's the Dinking diagram of SL3 up here. And then you just repeat it from plus infinity to minus infinity in the vertical direction, and everything here are oriented cycles if I didn't make a mistake in drawing. That's the quiver for the T system. And to get the quiver for the Q system, that's a finite rank cluster algebra. You just fold this on a cylinder of radius 2. That's what the effect of forgetting about J. So this is, for example, this is A3, type A3, Q system. Okay, and here's the statement again. These are all discrete evolution equations in time k. They're all integrable. They have Poisson commuting Hamiltonians, n minus 1 of them, which are independent of the k, the time variable. They're all cluster algebras, as I said. And therefore, they have a canonical quantization. And so this equation has a canonical quantum version. So the q variables become non-commuting. Okay, so you know where this is going. I can do this for every affine Lie algebra. So it's possible to solve the type A systems explicitly. It's possible to write down the commuting Hamiltonians, and it's possible to write down the solutions. But you have to work hard, and it's a combinatorial solution. And I want a somewhat more uniform solution that will generalize to all the root systems. And in particular, what I wrote here are the affine root systems. So these are the classical ones you might be aware of. These are the twisted ones. All of these, apart from type A, are controlled by a BC type Weil group. So they have something in common here. And they have to do with Kornwender operators or polynomials. And so in the notation of Macdonald, you can find Macdonald. If you drop the affine root, you get a root system, a finite root system. So for type A, you get SLN. For type B, you get Bn, and so on. These are the Katz notation for the affine root system, and these are the root systems R. And then there's R star, which you also have to consider. R star is equal to R, except in types B and C. Otherwise, it's the Langlands dual. Okay, so I have this zoo of root systems. You don't have to memorize this, but I have this in the back of my mind, and I want to find a method for solution. So I want to prove integrability and so forth for all of these root systems at once, or in the same way. Okay. So the Q systems exist. They were written down. So Kirillov-Reshetykhin, I think Kuniba, Nakanishi, and Suzuki, Hatayama et al. Okay, these have existed in the literature for a while. So again, you have a commuting family of transfer matrices. You take the asymptotic limit of the TBA, and this is what you get this Q system. And mostly it looks exactly the same. It's a discrete evolution in time variable K. And it's a two-step recursion relation for the most part. And so on the right-hand side here, you get a monomial. And this monomial depends on the root system you're talking about. And most of the time, this monomial just depends on the Cartan matrix of R. R is this root system here. Except in some exceptional cases, which cause a lot of headache. But I just want you to notice that this term just is another monomial. But it just, there's some slight differences. So it depends on the structure of the root system. So one has to keep this in mind. And most of the time, these are cluster algebra mutations, except for this last case. A2 and 2 is well known to be a troublesome affine algebra. But apart from that, they're all cluster algebra mutations. So there's a cluster algebra behind all of these. And these are all integrable. And we want to prove this for all affine root systems. We want to find the commuting Hamiltonians, Poisson commuting Hamiltonians. And then there's a quantization, either because they're cluster algebra, or in this case, because you can tweak them to make a quantum system. So we have other guidelines as to how to quantize it. There is no canonical quantization for type A2 and 2, but it's not important. And so we want to actually find solutions for the quantum Q systems in terms of Q difference operators and the Hamiltonians. And then the unifying framework, we claim, have to do with McDonald-Cornwinder operators. So I want to explain how that works. So go. Okay, so first of all, the quantization, what does it look like? Okay, so you need to know something about root systems and weight systems to see that. But here's how you quantize a Q system. First of all, you have to say how these variables are non-commuting. In the cluster algebras, these are cluster variables. If they're in the same cluster, they all Q commute. So they have sort of nice commutation relations. So the Q commute with some factor of Q. It has to do with the inverse Cartan matrix, lambda, usually. And then the evolution equations, they look almost the same, except that this monomial might consist of non-commuting variables. And so in that case, you should consider them in a normal ordered way. So it looks exactly the same, except there's a factor of Q here, and there's a normal ordering here, which just means an overall factor of Q. So in type A, this is all you have to know. So neighboring K's Q commute with the matrix min AB. Min AB is closely related to the inverse Cartan matrix of SLN. And the evolution equations for these non-commuting variables just have a Q to the A here. Turns out that here, these two, they commute. So in fact, it's a very simple system for type A. It looks almost identical. Okay, so I've quantized my systems. And here's what I want to do. For each affine root systems, I want to prove the integrability, find the Hamiltonians, and find the solutions of the quantum Q system in terms of Q difference operators. And they turn out to be in this in the representation of the spherical double affine Hecky algebras. So this program works for all the root systems that I showed you. And the ingredients are, there's a duality in McDonald theory, which is a very beautiful property, which I want to show you. And then I use something which, okay, it's not a Fourier transform, but it's close. To go from McDonald eigenvalue equations to Peary rules to find the Hamiltonians. And then also on the double affine Hecky algebra, there's an SL2Z action. And one of the two generators of SL2Z will turn out to be the time translation operator. So I need to say how it acts on this algebra. And then I will explain that all of this quantum Q systems have to do with, in fact, the Q Whitaker limit of McDonald theory. So it's a slightly less symmetric theory than McDonald theory. You go up to McDonald theory because it has all this symmetry, it has duality and everything. So here's how it works. So here in type A, and I will just explain this in type A, and then I'll just flash how it generalizes to other types. In type A, McDonald wrote down commuting difference operators. So dA, A goes from 1 to n. So you have a rational function in the variable x. Here's capital X means the variables x1 through xn. So it's my shorthand. So whenever you see these capital letters, they have to do with a multivariable. And gamma I is the Q difference operator. So gamma I xj gets a Q if j is in the subset I is a subset of 1 through n. So gamma is a Q difference operator. So it's the product of several Q difference operators in xi. So this is a way of writing down McDonald's commuting difference operators. They're elements in the functional representation of the double affine Hertzian algebra, and the spherical part of it means that because they're symmetric, they're invariant under permutations, or they're invariant under the Hertzian algebra. McDonald's eigenvalue equation, at least the first one, is that D1 acting on P lambda of X has an eigenvalue. E1 is the first elementary symmetric function in the variables S. So S is Q to the lambda T to n minus I. So this is a multivariable. So it's just the sum of these S's, the first elementary symmetric function in this case. And this equation has a unique monic polynomial solution called the McDonald polynomial if lambda is an integer partition. So lambda is a dominant integral weight of SLN, in other words. Yes, invariant under the action of the symmetric group. So spherical just refers to the fact that it's a symmetric part. So I don't actually have the operators that exchange variables. That's projected out. So in the spherical Daha, you take whatever you have in Daha and you project on the left and on the right by the symmetrizer. So yeah. Okay, so this equation, on the other hand, has something called universal solutions. So I learned this from Shiraishi actually, but apparently this was in the literature in some form. So instead of lambda, so you see x is a multivariable x1 through xn, and lambda parameterizes a weight. So it's lambda 1 through lambda n. But we consider it to be a bunch of integers, right? It's an integer partition. Instead, we want to consider lambda and x on equal footing. And how would we do that? We look at these variables si and we just say, okay, we just make them into arbitrary complex numbers or formal variables. So lambda doesn't have to be an integer. And if we do that, we just write down, instead of p lambda of x, we write p of x and s in this nice suggestive notation. So this takes a while, it takes some getting used to. So I just consider S to be formal variables and I write down the same equation, the same eigenvalue equation. D1 acting on this thing is E1, the first elementary symmetric function acting on this thing, except now S's are formal variables. And because D, you can take this rational function and expand it in some direction. So if I choose to expand it in the direction in terms of xi plus 1 over xi, that's xi to the minus the fundamental, the simple weights of SLN. Okay, I can choose to expand this rational function as an infinite series in these variables. Then this is a triangular system, and it can be solved term by term. It has a series solution. It's unique up to scalar multiple. And if I choose the series to start with Q to some power, so this power is just x to the lambda essentially. So if I parameterize x in the same way that I parameterized s in terms of, instead of lambda, I parameterize it in terms of nu, there's a unique solution to this equation in terms of a series in x, where x to the minus alpha. So beta here is in the negative or in the positive root lattice because it's x to the minus beta. It's a triangular system and you can solve it for these coefficients. So if you pick C0, then the solution is uniquely defined. That's the scalar, C0. Okay, this might look complicated. This is called the universal solution, and here's the reason. There's a natural normalization that you can pick for this thing. You can pick C0 to be 1, and whenever lambda is an integer partition or a dominant integral weight, this series actually truncates. These coefficients become 0 after a while, and this becomes a polynomial, and the prefactor ensures that it's in fact a symmetric polynomial, and it's the Macdonald polynomial. So this normalization, C0 is equal to 1, under this specialization truncates to the Macdonald polynomial. Any Macdonald polynomial for any lambda is contained in this series solution. So for that reason, this is called the universal function, the universal Macdonald function. On the other hand, there's a more natural normalization if you want to talk about duality, so self-dual solution. So it's another normalization. You pick C0 to be this function delta. Okay, what is this function delta? You take the root system of type A, you take all the roots of type A, so this is a finite product, and then infinite product over n, this ratio. It's almost 1. When t goes to 1, it's 1. This is called delta of S. And if you normalize C0 to be delta, then P2, they're self-dual. So if you exchange the parameters x and s, you have this symmetry. This is called the Macdonald duality. So Macdonald didn't write it this way. Macdonald wrote it only when mu, remember mu parameterizes x and lambda parameterizes the weight. It parameterizes s. Macdonald wrote down this equation. When mu and lambda are both integer partitions, this is Macdonald's duality. And so this is the duality for the universal function. And as far as I know, Macdonald didn't know about this, but possibly Cherednik knew about this, and definitely Naomi and Shirishi proved it explicitly by computing explicitly this function. Okay, so we have this beautiful duality property. And you can use it to derive the Peary rules from the Macdonald equation. And this Macdonald did know. If you start out with the eigenvalue equation, and I'll pick the second normalization here because it's self-dual, and I just rewrite the variables. Instead of x, I write s, and instead of s, I write x. So it's just this, obviously. And then I use this duality symmetry. Then I get this equation. So D now is a Q difference operator in the variables s instead of the variables x. And so if I specialize this equation, so here I have the elementary symmetric function, the eighth elementary symmetric function in x now. Now if I specialize s to be, integer partitions, so it's a discrete variable, then I get the Peary rule, h, which is some renormalization of this. So, okay, I've hidden a bunch of normalizations. So H is in fact, you take D of S and you act with delta, you act with an adjoint action of delta of S. Doesn't commute with D of S because now D is a Q difference operator in S. Okay, and then you normalize with T to the lambda. And you get this equation, and these are the Peary operators. So what happens to the Macdonald symmetric polynomial when you multiply it by the eighth elementary symmetric function? That's the Peary equation. And these operators are Q difference operators in lambda or S that accomplish this. Okay, again, this equation, let's say 2, it has or this equation, it has a unique solution as a series now in S, because this is a Q difference operator in S in the same way that the Macdonald operator was a Q difference operator in X. This is a triangular system for the coefficients in an infinite series in S, and you can solve it. And so you have an infinite series in S, and it should be equal to the infinite series in X if you picked your normalizations correctly. So analytically, it's not obvious what that means exactly, but whenever you specialize the integer partitions, that's certainly true. So without considering questions of convergence or anything like that, you have a series in S is equal to a series in X. Okay, then there's something called the Whitaker limit, and most people here don't know what a Whitaker limit is. So here's the picture of the Macdonald world. So Macdonald polynomials, P lambda that I wrote down, they have the symmetry. You go from QT to Q inverse, there's a symmetry. And so if you draw Q on this axis and T on this axis, then it goes from 0 to infinity in Q and 0 to infinity in T, and 1 is in the middle here. If Q is equal to T, Macdonald polynomials specialize to Shor functions. This is known. If you take Q to 0, you get Hall-Littlewood functions. They're functions of T. But on the other hand, because of the symmetry, if you take Q to infinity, you'll get Hall-Littlewood functions of T in the parameter T inverse. And then these, you have the elementary symmetric functions here, you have the monomial symmetric functions here, but on these two axes, so that is Q is equal to 0 and Q is equal to infinity, you have the Q Whitaker polynomials, in fact. So whatever you get from Macdonald polynomials when T either goes to 0 or infinity, I'm going to call Q Whitaker functions. So it's a name for this particular audience. And so here you'll get Q Whitaker polynomials as a function of Q, and here of Q inverse because of, again, this symmetry. So I'm interested in this limit on the right-hand side because it's convenient to take. There's no particular reason why we didn't take T goes to 0, but this is what we took. So this is what I mean by this limit. Okay, so but in this Q Whitaker limit, which has to do with the quantum Q system, we lose some symmetry because, for example, these functions delta of S, because S depends on T, you only keep the dominant term when you take the limit T going to infinity. In fact, delta of S goes to 1 in the Q Whitaker limit. Whereas delta of X doesn't, but it does simplify. It becomes a product over only the simple roots of SLN. And again, it's an infinite product in Q. You probably don't remember, but delta of X had to do with a product over all positive roots. And now in this limit, we only get the simple roots. Okay, it's a simplification. And then what happens to this beautiful symmetric duality of Macdonald is, well, it doesn't look as symmetric anymore because in here, if you remember, there's a relative function delta. And delta of S goes to 1 and delta of X goes to delta bar of X. And so it starts looking like this. You have a function pi of X and lambda is equal to delta bar of X times this function capital kappa, which is K of lambda and X. And here, this capital lambda is just a way of parameterizing Q to the lambda. That's the variable we should consider. So this is what remains of Macdonald's duality in the Q Whitaker limit. Nevertheless, this is a perfectly fine limit, and I can take both the limit of the Macdonald equations and of the Pierre rule, and I'll get two different rules in this limit. The first one is an eigenvalue equation. The eigenvalue equation here, remember, there was an element, the first element, or the 8th elementary symmetric function in S. And as I explained, S, you only keep the dominant term, that's S1. And so what happens is this is no longer a symmetric function. This is just lambda to the omega A. So for example, if this is 1, this is lambda 1, so Q to the lambda 1. For type A, omega A is just the sum of the first A basis vectors. So this is not a symmetric function anymore. Nothing happens much to these Macdonald operators. They don't really simplify. I mean, so now it's a monomial on top. It's not much simpler. It's still a rational function. So these difference operators, they're still Q difference operators. And they're still rational functions. They don't simplify. Nevertheless, so there is a unique series solution to this equation in X with a leading term, which I like to write X to lambda. So you take a sum over the positive root lattice, some coefficients which depend on lambda, and X to the minus beta. And if I choose C0 to be 1, this truncates when lambda is an integer partition to some symmetric polynomial. It's still symmetric. And it's a class 1 Q Whitaker polynomial. Okay, it's a name, but it's a polynomial in X. Okay, so these are the eigenvalue equations. And then what happens to the Peary rules in the Whitaker limit? So actually H simplifies a lot. It's no longer a rational function. H1, for example, is this sum of n terms. And I'll explain in a second. But on the right-hand side, I maintain the elementary symmetric function in x. Nothing happens to x when t goes to infinity. So this is still symmetric on the right-hand side. So what is this? This is the Q difference operator in t and lambda. So t is the Q difference operator in lambda. So if I write, so this should be tj lambda I. So t translates lambda by a factor of q. So instead of x and gamma, I write lambda and t. So I have two quantum tori around. X and gamma describe a quantum torus, and lambda and t describe a quantum torus. And this is what I mean by quantum torus. So these, what happened in this Whitaker limit is that these Peary operators became no longer rational functions and Laurent polynomials in lambda. So they're very, very much simpler, and one can actually work with them. So these are commuting operators. There are, I guess there are n of them. And this equation, this Peary equation, has a unique solution in terms of a series, again, in lambda this time. So again, sum over the positive root lattice, lambda to the minus beta times some coefficient. And if you choose to normalize the first coefficient C0 to be 1, then you'll get an infinite series. There's no truncation that goes on. And these are known as fundamental Whitaker functions. So you get their relation with the Whitaker polynomials is via the function delta. So this infinite product. So if you know about Whitaker functions, they have to do with some highest weight. The weight is now parameterized by x instead of lambda. Okay, and then there's this other beautiful fact about the Daha. The Daha has an SL2Z symmetry. And how it acts on the polynomial representation is by an adjoint action of a quantum dilogarithm that looks like this. You don't have to know what this is. You just have to know that if you act on x, it doesn't do anything. This commutes with x. And if you act on the Q difference operator gamma in x, you get a factor out of x. So all you have to know about this gamma is that its adjoint action does this. So it's a very simple action. It's not actually an element in the Daha, but it acts on the Daha. And it preserves the symmetric part of Daha, the spherical Daha part. So I claim that this, for me, is the time translation operator. If I define dAx to be the adjoint action of lambda to the k acting on the McDonald operator in the Whitaker limit, these actually are the solutions of the quantum Q system, I claim. So this is a combinatorial statement. So I have a bunch of fairly simple or complicated looking Q difference operators, and one can actually work with them explicitly. And it's rather difficult, and it's kind of a miracle, the fact that they satisfy this quantum Q system. We proved this with Philippe in 2019 via explicit computation. But this computation is difficult, and it's not fun to generalize it to other root systems. So we were proof that actually gives us more, like why is this true, and generalizes to other root systems. So this is the proof. So first of all, this is the second useful trick I wanted to show you. So these universal functions are complete in the following sense. If you have a bunch of Q difference operators, fi of x, acting on x, that act on the universal function, for example, by some, you can call this eigenvalue, but it's not really an eigenvalue because fi hat is a Q difference operator in lambda. So a Q difference operator in x acting on pi is a Q difference operator in lambda acting on pi. So the relation is fi goes to fi hat. Then I call this the Fourier transform. And if these Q difference operators satisfy some relation, then then these fi satisfies the same relation with the opposite multiplication because of completeness. Well, it turns out that the lambda side is much easier to work with because of the simpler form of the Hamiltonian. The Hamiltonian set, or the Peary operators simplified a great deal in this limit. So I'm going to define d hat ak. So k, remember, is my time variable and a is my flavor, as follows. So the initial data is that the first one is just the Fourier transform of the Macdonald operator, and its eigenvalue we know was lambda to the omega. This is simpler than the Macdonald eigenvalue because it's monomial. It's instead of a symmetric function, and this is what makes this engine run. And then I say, okay, I need to solve the Q system, I need two initial data, so 0 and 1. So the second one is just going to be another monomial in lambda and t. T now is a Q difference operator in lambda. And all the other ones then are uniquely determined from this equation. K is negative or positive, it doesn't matter. Just it has to be a solution of this system with the opposite multiplication. This is the system with the opposite multiplication. It uniquely defines these operators. And because this is a cluster algebra mutations, these are in fact Laurent polynomials in these two things, and therefore it's just a Laurent polynomial. So it's not a rational function in the lambda variables. Okay, so we already know that this equation holds for k equals 0. That's just the Macdonald eigenvalue equation in the Whitaker limit. And so then what do we do? So the theorem is that there is a unique time translation operator G, such that if I act on d hat with G, so it's a Q difference operator in T in lambda. If I act on the d hat, I'll get d hat of k plus 1. So what I'm saying here is that I determine G from the Q system. So from this system, I can compute G. The fact that G doesn't depend on K is not a given. It's consistent with this equation. I just have to do this for the first two steps, and it completely determines G. So it's a calculation, and this is the explicit answer. This is in fact the product of quantum dilogarithms. And also, the second part of the theorem is that this G actually commutes with the quantum toda Hamiltonian. So in some sense, it generates, in fact, all the Hamiltonians. So these two things are explicit computations. And the third statement is that G is the Fourier transform of the Gaussian gamma, which was the SL2Z action. So 1 and 2, as I said, are by explicit computation, just using the quantum Q system and the Hamiltonians. And the third statement has to do, so if you start with the Peary rule, H1 on the Whitaker function is an eigenvalue times the Whitaker function. And remember that this has a unique solution up to normalization. Since G commutes with the Hamiltonian, you can act on this equation. And so you see that G times the Q Whitaker function is another eigenfunction. So it should be proportional to the Q Whitaker function. And then you compute the proportionality constant from the form of the series expansion. And it turns out that the proportionality constant is just gamma. So this is a proportionality constant. It's a constant with respect to lambda. It's independent of lambda. Okay, so as a corollary, the Fourier transform of d hat at time k is just d at time k, and it is a solution of the quantum Q system. And because G is the time translation operator, it commutes with the Hamiltonians. Therefore, these Hamiltonians are the conserved quantities of the quantum Q systems. And in fact, from their explicit form, they're relativistic quantum toda Hamiltonians. One can recognize them as being such. Okay, so that was the end of the story for type A. And this is the proof that generalizes to other types. And this is the zoo of other types. So now I'm going to just flash these slides. What happens in other types is that there are Kornwinder operators. And then there's higher Q difference operators for this theory by Van Degen and other McDonald also and others. And these depend on some parameters, which when you specialize them, you get the other affine root systems. So this one is new. Okay, it wasn't in McDonald. We don't know where it came from, but some specialization. And the Kornwender operators, they're different from the McDonald operators. Instead of having the symmetric group is the file group, the symmetric group here is the C-type group. So exchange of variables and inversions. So it's a BC symmetric. So the eigen functions are BC symmetric, elementary symmetric functions, and the Kornwender polynomials are BC symmetric polynomials. So they're polynomials in X and X inverse. Okay, so then we repeat the same program given this data and find the time translation operators from the quantum Q system in the Q Whitaker limit for each affine root system. And okay, I just flashed what the first Kornwender operator looks like. And the first, okay, the only thing I wanted you to get here is that the eigen values of the Kornwender operators are elementary symmetric functions. So this is E1 is just the sum of S and S inverse, same S. Well, okay. And again, this has a unique series solution called the universal function. And again, it has this duality property. The duality property is sometimes new. So it's new for the universal function. Van Degen and Sahi and possibly Cherednik proved this for each of the root systems, so for the specializations, but in fact, it's true for A, B, C, D arbitrary. So again, you have two normalizations for Kornwender universal solutions, and the second one is self-dual. And self-dual here, the parameters A, B, C, D have some dual, A star, B star, etc. And that's responsible for the root system going to the Langland's dual root system. Okay, so we repeat the same program. We use the eigenvalue equation and the Pierre rules for Kornwender polynomials, specialize and take the Q Whitaker limits. We get commuting Hamiltonians. And so now we have the commuting Hamiltonian for each affine root system. And so some of these are new and some of these were known before. They come from, oops. I think my computer went to sleep or something. Or ran out of energy. Is there a charger? Is there a charger?
What is it? What for laptop is it?
Apple.
Apple. Does anyone have an Apple charger?
This is the wrong charger. Ah, thank you. Oh, it's because I'm running Zoom and it's I'm sorry. This gives you time to ask questions.
Okay, so while the laptop is rebooting, are there any questions?
So I think I remember from at the start of the talk, you were showing these Q systems for maybe twisted types or something where you had the red correction terms. And in particular on the right-hand side, it contained 2K. So it kind of, if you want to, it seems weird if you want to reinterpret this as a time evolution because your step actually depends.
Right. So yes, so it depends on the root length and it's actually not in the twisted type, but the untwisted type. Types BC depends on the root length. And so what happens is that some variables for some, can you try and make that thing up? For some roots, the variables actually move faster. So the time variable moves twice as fast for some colors.
And you can still kind of
but yeah, so a cluster consists of variables, some of them, so it's just different parameters. The time variable is different for different colors, in fact, for non-simply laced root systems. So that will be true in any non-simply laced. Why is it not two? But why isn't it? What's the matter? It's not charging?
It is charging just a bit slow.
This is not normal. Yes. So yeah, it is true. The times runs twice as fast for short roots in types BC. So I don't know what the quasi-polynomial Macdonald functions, but the Macdonald polynomials of types BC are Laurent polynomials. So they're polynomials in X and X inverse. And so they're symmetric under exchange variables, and also under exchange X goes to X inverse. Is that what you mean? So otherwise I don't know. Non-integral weights, yeah, okay. Yeah, so they're not, so it's not working up. Okay, I don't know, this is not normal. This is not normal for this computer. You broke my computer. Okay, maybe I'll just. I know, why don't we? No, just remove, no, remove. Oh. Okay, well. Yeah, so if it doesn't wake up, here's what I want to say, unless people have questions. So what I wanted to say is, so this function G that I computed, which accomplishes time translation, and you know, when I have two different root lengths, there are two different functions G, for example. It accomplishes time translation for these root systems. I should say all the time we spent on this was on this non-simply laced types because of all these complications. It is a specialization at a particular value of the spectral parameter of the Baxter Q operator. The Baxter Q operator in some other way. Okay, so Schrader and Shapiro wrote down such an animal. It is a generating function for commuting Hamiltonians. You can view it as a generating function for commuting Hamiltonians. So the fact, in that case, the fact G commutes with the Hamiltonians becomes natural. You can look at G as a specialization of a Baxter Q operator. At least in type A, this is correct. What else did I want to say? I don't know, I don't have my slides. And then I wanted to finish with the homework, which is I did all of this for the classical root systems. I have not done anything for the exceptional types. So that's the homework. I think I'll give up on this computer, it's dead.
All right, thanks very much, Rinat. Let's so the slides will be shared at some point, so we can still
if I can wake this up. Yeah, that's true. I have to. You're talking about the X picture, the Whitaker limit of the Macdonald operators. Still a triangular system, so you can still expand in powers of X to the minus alpha.
Right, but if by chance say that your eigenfunctions are for the particular one.
Yes. Ah, yes. 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 So my claim is that if I pick the form of the solution to start with x to the lambda, then there is a unique solution that you can write down as a path, for example, solution for the coefficients, because it's a triangular system. And it's not the eigenvalue, it's the form of the operator that gives you this path solution. Yeah. Yes, so in McDonald case, you use the eigenvalue to distinguish between eigenfunctions. And for the universal function, this all is, McDonald polynomials are all specializations of the same universal function. The eigenvalue depends on this specialization, right? So when you specialize, in fact, you don't see this. Yeah.
The question myself, though. Is there a sort of an analog on the non-symmetric case?
That's a very good question.
Well, because there the eigenvalue is also special.
Yes. Yes. Yeah. Yeah. So Cherednik also asked us this question, but we don't actually know how to approach this because, of course, the Q difference operators are much more complicated. So maybe the picture is not as nice when they're non-symmetric. I know this is an important question. Yeah.
Battery of this is also on.
The battery that. So we're just a bad day for batteries, all in all.
Let's thank Rinat again. And
Thank
then
you.
we'll convene at